A fairly short talk, but I want to tell you a bit about how we validate OpenMM to make sure it's working correctly. And validation means a few things. First, and perhaps most obviously, we want to make sure that when you run it, it doesn't crash, because if it crashes, that's not very useful to you. But it also means that it produces correct results. And it's actually very complicated to test because we have a really huge testing matrix. First of all, we support across a lot of different operating systems, Mac, Windows, Linux, but then you have, many different versions of each of those. Mac, we have people running on everything, Snow Leopard, Lion, Mountain Lion. Windows, we've got XP, Vista, Windows 7. Soon there will be Windows 8. Tons of different distributions of Linux. All of these, we have 32 and 64-bit versions of the operating systems. So just that one axis of our test matrix is huge. Then we have different types of GPUs. We support both NVIDIA and AMD GPUs. In the near future, we'll be supporting Intel GPUs. But then every one of those has different models. So, even just like NVIDIA GPUs, you've got, everything from G80 up to Kepler generations. So it's like 5 different generations of GPUs, et cetera. Then for OpenCL, we have several different implementations of it. NVIDIA has an implementation, AMD has an implementation, Apple has their own implementation which supports both NVIDIA and AMD GPUs. Intel has their own implementation. And so it's really a huge test matrix, and we can't even hope to actually test on every possible combination of all of these things. But we try to pick a reasonable set of systems that we can test on that will get some reasonable combination of what people are most likely to be using, and then provide tests so you can do the validation yourself on your actual hardware. So the first type of testing that we have is called unit tests. A unit test is a piece of code designed to test some very small, very specific feature of a program. It's a unit of code. Most of our unit tests are very simple. They'll do something like simulate a single harmonic bond using a Verlet integrator and just compare the trajectory that produces to the known analytical result and see, is it giving us the correct trajectory that we expect. A few of them do more complicated things like, simulate a box of water at constant temperature and pressure and say, okay, is it giving us the average box volume that we physically expect it to have? Is the kinetic energy averaging out to the right value? So we have many hundreds of unit tests. If you want to run them, they're all included with the source code. So if you build from source code, you can just type make test, and it will go and run through all of the unit tests. This is showing just a little bit of the output. And these numbers here, we're showing like of 160. Each one of these lines is actually a test suite, not a single test. So each one of those might have several different unit tests contained within it. So many hundreds of tests, and this will just give you a report on what passed and what didn't pass. And if anything fails, you can run them individually and get a more detailed error message to see what's failing. The second type of tests we have are what we call system tests. Whereas a unit test is designed to test one very specific small piece of functionality, a system test tries to validate the entire program as a whole, a broad slice of functionality using realistic usage cases that are typical of what users actually run, and see is the entire thing working as a whole. So all of the system tests are involved with, they use realistic test systems, proteins, DNA, RNA. We have ones with both implicit and explicit solvent, and they cover a huge range of system sizes. From the smallest ones are 75 atoms, all the way up to the biggest ones we've got are 173,000 atoms. And for each one of these, we have a series of different tests that we run, which I'll talk about in individually, but consistency across platforms, force energy consistency, and integrator accuracy. So the first type of test that we do is just to take the system, compute the force in every atom, and do it with each platform that we have and see if they all agree. Because if they're if there's because each one of them is an independent code base, chances are very high that if there's a bug in one, it won't be in all three. And so we just want to check and say, okay, does CUDA and reference give the same forces? Does OpenCL and reference give the same forces? And then we'll just go through every type of force involved in it and compute how well do they match. And all of these things, by the way, we have like big tables in the user guide that give the results of all of these. So if you want to see exactly how well different things are matching, and this is just sort of like a little excerpt from that table. The second type of test we do is force energy consistency. This is really just checking that you expect the force should be the gradient of the energy. So if you calculate the energy, you calculate the force. Do they agree with each other, what you expect? So we take the system, put it at a location, compute the force and energy, take a tiny step in the direction of the force, and evaluate the energy again. And did it change by the amount we expected it to? Because to first order, the change in energy should just be the size of the step times the gradient of the energy, which is the force. And so, again, we do this test, and you'll find a table in the manual listing for each one, how well did they agree. Third class of tests we do is tests of the integrators. For deterministic integrators like relay, we just check, is the energy conserved? Run a simulation and see, you expect the fluctuations in energy over the course of the simulation to fall below a threshold. And for stochastic integrators, we check the kinetic energy. You expect that the kinetic energy on average should be 1/2 kT per degree of freedom. So we just run a simulation, compute the average kinetic energy over it, and see if it's the correct value for the temperature. One more class of, I should have mentioned earlier, one more class of tests we do is to just compute forces and then compare them to forces that are computed by other programs. In particular, for the conventional force fields, we compare to GROMACS, and for Amoeba, we compare to Tinker. And we just go through all of the different types of forces and say how accurately do they agree. That's pretty much what we do. Any questions about it?
It might be helpful for folks to know for each category of numbers, like how, what is considered to be a small error?
Yeah. So that will vary on things. So generally with forces, we're computing forces mostly in single precision, which has machine epsilon of, I think, like about 3 × 10⁸. So, reasonably, you can expect that all the average forces across a large system should add up to an error probably of no more than about 10⁵. These are relative errors showing here. In the force energy consistency, the numbers are bigger because we're checking a relation that's only accurate to leading order. So, there's going to be a uncertainty just based on the size of the step that we took. Yeah?
If you have to recommend a robust system combination of what operating system, what GPU? From your point of view, because
Sure.
I'm going to be using it for students, I don't want to
Right. All right. I would definitely say an NVIDIA GPU. It depends what you mean by robust. Generally, so NVIDIA has the consumer level cards, and they have their scientific computing ones, the Tesla cards. The Tesla cards are much more expensive. They are a little bit slower. They have a bit more memory, and they're a bit more reliable. Really your call about which ones you want to use. They are
routine applications, standard applications for running a computational chemistry lab.
Especially if it's for students, you can probably get away with the less expensive consumer level ones. They cost like a quarter as much. So you're looking at $500 instead of $2,000. On the other hand, there is a slight the more expensive ones actually are a bit more robust. I'm not convinced that that's for any reason other than just that they've clocked them a bit slower. In terms of operating system, Linux is very much standard. The drivers are always a bit of an adventure on Linux, video drivers. Of course, drivers tend to be a bit of an adventure on any operating system. They're particularly an adventure on Linux, but it is a more robust operating system, for example, than Windows, and Windows or Mac have their own issues. Yep.
If we had a customized force field that customized potential function, does the code go through to see if the energy is conserved before starting the simulation?
So we, like,
So
if,
how about, my question is that, how about if you just threw some potential function which is not correct?
right.
What happens?
All right. So you're saying like with the custom forces? So a few answers to that. First of all, we certainly do have like unit tests for all the custom force classes. So we believe that the custom force classes work as they are designed to work. When you say a potential function that is not correct, what does that mean? It's not the potential that you really wanted, or what?
Something that you just make up.
You know, we do not know whether the thing you made up was really what you intended to make up. It will take whatever function you give it and assume it's what you meant.
Yeah, but the correct potential function should conserve energy
Oh,
at all times, right?
so with custom forces, so whether it conserves energy is basically a matter of is the force the gradient of the energy? And yes, the force will be the gradient of the energy. You give us a potential function, we analytically compute the gradient of it. So the force will be the gradient of the energy. Whether it's really the energy you wanted is another question. Now, one caveat to that, the force is only going to be the gradient of the energy if your energy does not have discontinuities in it. And you absolutely could write down a potential function that has discontinuities. And if you do that, then you're not going to get energy conservation. But we aren't going to say, you idiot, you obviously didn't really mean this, because for all we know, you really did intend to have those discontinuities there. Yeah.
What do you consider good energy conservation? Because we're talking numerical problems here as well.
I've just been writing up a paper about energy conservation, and one of my main conclusions is that all published numbers for energy conservation are nonsense and have no impact on whether your simulation is actually accurate. So given that, I'm a little hesitant to give any sort of number. Generally, you're going to be doing simulation at constant temperature. Given that what you want is that energy drift over the time scale on which your thermostat couples to the system should be negligible.
Yeah, but I was thinking if you test an MDE,
Right.
just for the sake of knowing how it's performing, if you mask it by a thermostat, you have no idea. I mean, you could have a huge drift and something
Right.
that's totally not working correctly, and you mask it.
Right. But even
So
when
in
you...
MDE, I was wondering what would be considered a reasonable number. Because,
I-
I mean, we find, for example, if you play around with cutoff, you take your real space cutoff, and if you go below 8.5 on a typical peptide, you start seeing significant drift. 8.5 is a magic number. Go to 9 or higher, it's fine.
Yeah.
PME, single precision, we found 10-fold more drift than in double precision.
Yeah.
Is that bad? I don't know. Maybe you're just introducing some noise. But
Yeah.
By energy, you mean the sum of kinetic and potential?
well, exactly what
energy, or
you're
just
mentioning, the energy should conserve. I mean, you have a system, Verlet conserves energy very well. You can take one bond and run it for days, months, millions and billions of steps, and it will still have the same energy. It might oscillate, but it will still have the energy at the end.
Yeah. Here, I mean, this is in some ways not a very satisfactory answer, but it's kind of the best answer I can give. Ultimately, you're trying to answer some scientific question, and what you really care about is, are the results that you are computing correct for some definition of correct? The answer, is going to depend very much on the details of your simulation. It will depend very much on what quantities you are trying to compute. For example, very often what you're really looking at is, you want to compute a distribution of states, a thermal distribution. And what you really want to know is, does your simulation produce the correct distribution that you expect? And that's a question that can be looked at very directly by, there are ways to test for your distribution and say, is this obeying the proper Boltzmann distribution that I expect it to have? But ultimately, every simulation really has to be validated. Okay, thank you very much.